So we're going to talk a little bit in this video about Taylor polynomials and where the coefficients come from. And we're going to start by investigating our tangent line, which is our first order Taylor approximation. Now what we're doing is we're basically forcing our Taylor polynomial to be equal to our function value at a and have the same first derivative at a. It can be checked very easily because p sub 1 of a equals, well, if I plug a in here, this is going to be 0, so this zeroes out, equals f of a. So they have the same function value at a. Alright, well, let's look at p sub 1 prime of x. This is just a constant, so it'd be 0, its derivative. This is some constant times x minus a, which is just linear. Derivative of x is 1, derivative of a is 0, so it's just f prime of a. Right, so our first order Taylor approximation is equal to our function at a and has the same slope at a. So what we do now is we take it to the next level. We say, okay, well, what if we want to have a quadratic term be the same? And so we're going to keep this part because this will still always be true. But we're going to add on some term here. Let's call this c1 times x minus a squared. A really quick check will show us that it's still equal at the first derivative and the original point. That'll always be true because of the x minus a nature. What we want is for it to be equal at the second derivative. So I need the second derivative of p sub 2, well, p prime of x. We already know that this is just going to be f prime of a. This is 0. This part's just f prime of a. We just did the derivative up here. The derivative of this is going to be plus 2c1 times x minus a, now to the first power. The second derivative at x, this is a constant, it goes away. It's just going to be 2c1 because the derivative of this is 1 and this is 0, so it's just left with 2c1. Now remember what we wanted. We want this to be equal to the second derivative of f at a. Well, in solving for c1, what that gives us is that c1 should be f double prime of a over 2. Alright, so if we want to add on a quadratic term, it should have an f double prime of a over 2. So we need f to be differentiable at least 2 times to get a second degree Taylor polynomial. A lot of the functions we'll deal with will have more than that as far as derivatives. I'm going to do one more of these to show you the pattern, and then we'll generalize it. Let's say we want to have a third degree term, p sub 3 of x. We already know that it'll be f of a plus f prime of a times x minus a. Plus, we've found the second degree term. It's f double prime of a over 2 times x minus a squared. Plus, now let's say we want a cubic term. All we need is c2 times x minus a cubed. That means we want to match up the third derivative of our function. We want to match this up with f triple prime of a. Well, let's see what happens when we start taking the derivatives. The third degree prime, this goes away. We know that that's just f prime of a. We've done this before. We know the 2's are going to cancel there, and we're going to get, oops, that should be a plus, f double prime of a times x minus a plus 3c2 times x minus a squared. Okay, now again we're trying to match up the third derivative, so I'm going to have to do a couple more. The second derivative, now this part goes away. This just becomes f double prime of a plus, and I'm not going to multiply these together just yet. I'm just going to write it as 2 times 3 c2 times x minus a, now to the first power. Again, this will still match up the way we want it to, because if I plug in a, then the third Taylor polynomial at a is the second derivative of the third Taylor polynomial at a is equal to the second derivative. So everything's still matching up real nice. Last thing we need is the third derivative And that's going to get rid of this. It's going to get rid of this. We're going to end up with 2 times 3 times C2. Now again, what we want is for 2 times 3 C2 to be equal to the third derivative at A. That means that this second term is F triple prime of A over 3 times 2. Without doing any work, we can probably imagine what the next coefficient would be. So for the fourth term, calling this next one C3, it would be the fourth derivative evaluated at A over 4 times 3 times 2, because these coefficients were coming from dropping down our exponents. Well, this is the third derivative at A over what we call 3 factorial, and this is the fourth derivative at A over 4 factorial. What this does is it gives us the general term for a Taylor polynomial. So, any given coefficient of a Taylor polynomial is going to be the nth derivative evaluated at A, where our Taylor polynomial is centered, over n factorial. Now, what we need to do is generalize this so that we can put it into our summation notation. So, if I use n here, n equals, not n, excuse me, k equals 0 to n, then the coefficient is going to be the kth derivative evaluated at A over k factorial, and then times x minus a to the k. So this will give us the nth degree Taylor polynomial centered at x equals a. And what we're going to do is now look at some properties of Taylor polynomials.